Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. I'm excited about today's video. This is something that I've been wanting to do for a long time. And that is, how did we determine the distance from the Earth to the Sun? So let's see how some very clever people over the ages have made a contribution to that. We'll dive into the math science history and unravel the mystery. And it all started with parallax. Lax! Now, the first serious attempt to find the distance from the Earth to the Sun was in about 300 BC by Aristarchus of Samos. Now, at the time of his observations, very little was known about the world around us. However, there were certain things that the ancient Greeks were pretty sure of, and that is that the surface of the Earth was curved and the shape that fit everything was a sphere. They also realized that both the Sun and the Moon were not part of the Earth. Aristarchus began to look at the phases of the moon to try and determine the distance to the sun, and he did it in a very elegant way. If an observer was to look up at the moon and see that it was either the first quarter or the last quarter, in other words, 50% of the moon was illuminated, that would mean that there is a right angle between the observer on the Earth and the sun, with the moon at the apex of that angle. Now, if the sun was an infinite distance away, this angle, this 90-degree angle, would also be 90 degrees to the observer on the Earth. In other words, it would be directly overhead. And these rays right here would be parallel. However, if the sun was not in an infinite distance away, these legs of the triangle would no longer be parallel. They would, in fact, form a triangle, a right triangle. And if he could determine the distance from 90 degrees vertical, he could actually calculate the distance of this leg of the triangle, which is the Earth-Sun distance. And he would calculate it in terms of the distance from the Earth to the Moon. So heading over to Math Portal for the right triangle calculator with detailed explanation, we can actually put these numbers in. Now, he got 87 degrees for the angle to the half moon. That would be this angle right here, angle beta. The distance to the moon is B to C, and we'll put in 1. Now, what we want to do is we want to solve the distance from the Earth to the Sun, which is the hypotenuse, C. So let's go see what happens. And we come up with an answer of 19 times the distance from the Earth to the moon is the distance from the Earth to the Sun. His geometry was correct, but his measurements were flawed. It's the old adage in science, measure it with a micrometer, mark it with a stick of chalk, and then cut it with an axe. It's not just how good your geometry is, it's whether or not your measurements are up to the task. Now, the problem that Aristarchus ran into is he didn't have the instrumentation that we have now. He had to visually guess when the moon was at its first or last quarter, half illuminated. Not 48%, not 51%, exactly 50% illuminated, and that was the source of error. And then he had to do a rather crude measurement of the angle from his zenith of 90 degrees to the center of the moon, and he came up with a number of 87 degrees. I've seen reports of 87 to 89 degrees, but we're going to use 87 in this case. Now, the first time that the actual distance between the Earth and the Moon was measured was with Project Diana in 1946. This was a government radar facility in New Jersey with a very powerful antenna. They decided one day to just check it out and see what it could do. So they pointed it at the moon. Lo and behold, they got a radar return, and it was 238,000 miles. So let's go ahead and use modern numbers with this. Our current measurement of the angle of Aristarchus is 89.85 degrees. And from our radar data on Project Diana, we have a distance to the moon of 238,000 miles. And we're going to solve for the distance from Earth to the Sun. Let's see what that comes up. Looks like it's just shy of 91 million miles. Let's see how that compares with the actual numbers. 93.114 million miles. The next major advancement in determining the distance from the Earth to the Sun came from Johannes Kepler. Now, Kepler reviewed a lifetime of data collected by the Danish astronomer Tycho Brahe and came up with his three laws of planetary motion between 1609 and 1618. According to the third law of planetary motion, the orbital time squared is related to the orbital radius cubed. Orbital radius will be in astronomical units, and time squared is in Earth years. Now here's that pesky little related to symbol that we see in Newton's original law of universal gravitation, where he said the force of gravity was related to mass 1 times mass 2 over radius squared. Now, in order to make this an equal sign, what we need is what's called a constant of proportionality. And that's what we see derived up here. And there is a constant of proportionality. Now, the key contribution of Kepler, as related to our discussion today, is his ability to predict transits of the inner planets, Mercury and Venus. A transit is when an observer on Earth sees either Mercury or Venus pass in front of the sun. Here's a transit of Mercury, and here is a transit of Venus. Now, a transit of Venus occurs twice in 120 years, about 8 years apart. The first time the transit of Venus was observed by people who actually knew what they were looking at and were planning on it was in 1631. In 1639, a young man by the name of Jeremiah Horrocks, just north of Liverpool, England, was the first to make a detailed observation of the transit of Venus and measure it. And this is his apparatus. Horrocks was 20 years old, and he used a telescope pointing at the sun to project an image on a sheet of paper. And as you can see right here is the little disk of Venus crossing the disk of the sun. And he was only able to observe it for about 2 hours out of the 6-hour and 40-minute transit. This is a reproduction of his observation. Now, as you can see, this disk right here of the silhouette of Venus against the disk of the sun. And he realized something. He could measure the size of the sun in arc minutes, and it came out to approximately 31 arc minutes. He was able to measure the disk of Venus at approximately 1 arc minute. Then he made a bold assumption. He made the assumption that Venus was approximately the same size as the planet Earth, with a diameter of about 8,000 miles. He was then able to look at the angular size of Venus and estimate the distance to Venus. Taking Kepler's third law into account, he was then able to estimate the distance to the sun. Using Horrocks' value of 1.3 arc minutes for the size of Venus and 8,000 miles for the diameter of the Earth, a quick visit to the triangle calculator determines the distance from Earth to Venus. Dividing that by 0.28 astronomical units, which is the distance from Earth to Venus, we come up with a distance of the Earth to the Sun of approximately 75,439,000 miles. Now, the fact that Horrocks got this value is actually quite remarkable. There are a couple of reasons for that. First of all, he made an educated guess that Venus was approximately the same size as Earth. It turns out that that's pretty much correct, but he really had no way of knowing it at the time. The second thing that's important to note is that he was a Puritan in 17th century England. He did this observation between church services. Fast forward to 1672, and we look away from the sun to Mars to help us determine 1 astronomical unit. The way that it was done was using something called the opposition of Mars. In the opposition of Mars, Earth is directly between Mars and the sun. It is at its closest point to Earth. And 2 groups of astronomers, one led by the Italian Giovanni Cassini and the other by the Englishman John Flamsteed. Both of them decided to use parallax to measure the distance from the Earth to Mars, again taking advantage of Kepler's laws of planetary motion to get a known distance between 2 planets and use that known distance to calculate 1 astronomical unit. They did it in 2 different ways. Both teams used the concept of something called parallax. Now, to look at Cassini's plan, he remained in Paris and he sent his colleague Jean Richter to South America. They attempted to both sight Mars on a particular day, and look at the stars that were the background. So for example, Richter, looking past Mars, would see, say, this star up here, which could be identified. Cassini in Paris saw another star, and that star could be identified. By looking at the number of arc seconds between these stars, they were able to determine this angle right here. Once they had that angle by the rule of similar triangles, they had this angle. They knew their baseline. Now they were able to triangulate the distance to Mars. Flemstead took a slightly different approach. He basically sat in his observatory and looked at Mars as soon as the sun set. He identified the star that was behind it. He then waited for the Earth to rotate and give him his distance, and observed Mars again just before dawn, finding another star. And again, he used the distance between those stars to determine the angle of this triangle. Even though both used parallax, they used different means to obtain that parallax. One used a physical separation on the Earth of a known distance. The other allowed the Earth's rotation to give them the distance. Both came up with essentially the same value for the distance from Earth to Mars in opposition, which is 0.52 astronomical units. And from that, they were both able to independently calculate 1 astronomical unit at being approximately 87 million miles. As a side note, this is an excellent demonstration of the fact that it is the Earth that is rotating, not the stars above us. This figure for an astronomical unit of 87 million miles stood for almost a century until a much more accurate method was developed. In our next episode, we'll talk about Sir Edmund Halley and the epic Transit of Venus survey of 1769. So until then, this is Bob the Science Guy signing out from Northern Michigan. I hope you'll join me for part 2 of this series because the Transit of Venus is a fascinating story.
This rabbit hole's too deep for me.